Hello everyone, welcome to the biggest ideas in the universe. I'm your host Sean Carroll, and we're continuing today our journey back up to the world of our everyday experience, to the macroscopic world of people and puppies and planets, from the microscopic world of fundamental physics, quantum field theory, and so forth. And today the big step we're going to take is to admit that none of us is Laplace's demon. We started this series many videos ago talking about the Clockwork Universe and our ability to, in principle, predict exactly what's going to happen. In practice, we're not able to do that. So what we'll be talking about are the concepts of probability and randomness. These are ideas that are both very important in physics, obviously, and science more broadly, but mathematicians have a lot to say, and philosophy has a lot to say as well. So there's subtle topics that we're not going to do complete justice to, but we'll get some of the basics across. And I want to start, let's remind you first about what the Clockwork Universe was, the universe that we thought was there in classical mechanics, and one in which, in principle, Newtonian Laplacian mechanics, you might want to call it. Giving Laplace some credit here because he's the one who came up with the idea of Laplace's demon, a vast intellect that could know, in principle, the position and velocity of every particle, and from that make predictions both about the future and retrodictions about the past. Okay, so this is a certain viewpoint on the world. Now we know that quantum mechanics is going to mess this up a little bit, but we'll save that for later in this video. But the picture, you remember, was you have space at some time, so time is going up, and there's going to be some stuff in the universe which is going to evolve, from these particles moving with these velocities to some other set of particles moving with different velocities, and the laws of physics get us there. And the relevant law of physics here is simply F equals ma. The force is mass times acceleration, in other words, the mass of the particle times the second derivative of its position with respect to time. First derivative is the velocity, second derivative is the acceleration. And the point is, if you have a bunch of particles interacting through some forces, and you tell me their positions and their velocities, this equation tells you how the velocity changes instantaneously over time. So in principle, I can use calculus to chug forward or backward in time and figure out what the system is going to do, the whole system, if it's a closed system, if I know everything that's going on inside it. So I actually, so we're going to talk about deviations from this viewpoint. I mean, not that this viewpoint is wrong. In classical mechanics, if classical mechanics were true, this would have been correct, but it's not the whole story because we're not Laplace's demon. We don't know the positions and velocities of everything. So can we do something, or are we just stuck in being able to say nothing at all? But before I do that, I want to give you a footnote. It's bad to start the video or an essay or a lecture or anything like that with a footnote that is kind of an aside. But in this case, I think it's kind of a very important conceptual point. And that point is that even this Newtonian system, classical mechanics, is actually not deterministic in the way that you might have hoped. We've talked about it as if it is. It turns out when you get into the equations a little bit more carefully, you find that this hoped-for determinism isn't quite there. It is almost there. In fact, technically speaking, it is almost always there, but it's not always there. And to show you that, let's give you a counterexample. There's a famous counterexample called Nortons Dome. John Norton is a philosopher of science, University of Pittsburgh. He's alive, contemporary guy. Hi, John, if you're listening to this. So he wrote a paper about causality, and he suggested this as an example of when it would be hard to pinpoint the cause of something happening. And the idea behind Norton's Dome is it's just a classical mechanical system. It's in spherical Cal-land, so there's no friction, there's no air resistance, nothing like that. And we are literally considering a dome, so by which we mean some sort of structure, architectural structure, okay, in the shape of a dome, and there's a point on top, and this dome has a very specific shape. So if you call the height h, I don't know why he did this, but h is the distance down from the top of the dome. There's a specific formula for the height as a function of r, the distance you are away from the middle, and h goes as 2 over 3g r to the 3 halves, where g is the acceleration due to gravity, so we're just having a dome in Earth's gravity. That's 9.8 meters per second squared, for those of you who remember your high school physics, right? The acceleration due to gravity. So Of course, there is a kind of trajectory for a particle. Let's put this in color so you can see it. There are kinds of trajectories for particles that just sit exactly at the top of the dome forever. So remember, we're not including quantum mechanics, no quantum fluctuations. We're not including air resistance or random motions of molecules. We're being completely thought experimenty and saying that in principle, a ball, frictionless, could sit exactly at the top forever. Okay, no one is surprised by that, but it's unlikely to happen in the real world. It's like trying to balance a pencil on your desk exactly. It's hard to do in the real world. It requires strictly infinite precision in putting it there, which is hard to achieve in reality. There are also, of course, trajectories where the ball rolls down the hill. And what Norton showed was that if you, with this particular shape of the dome, and there's some other shapes that also work, but a typical generic shape would not work. This is one that does. You get the following property, that there are solutions where the ball literally sits stationary, not moving a little bit, not moving at all, okay? It's just sitting there stationary, and then it starts to roll down. And this is happening without any force. This is why he was talking about it in a paper on causality. Nothing started it happening, okay? Nothing pushed it. It just suddenly starts rolling down with a certain trajectory as a function of time. And everywhere, including at that moment when it starts moving, it solves Newton's equations, okay? It solves the F equals ma equation. You can figure out what the force is due to gravity on a dome of this size, and of this size and shape. And what happens is, the reason why it's possible is because at that point where it just starts moving, the position is 0, r equals 0, okay, it's just sitting there at the top. The velocity is 0, it hasn't started moving yet, and the acceleration is 0, because there's no force acting on it, it's right at the top of the dome. But the third derivative of the position with respect to time is not 0 in this particular solution that Norton was able to find, which means that if you wait some finite time later, the ball will have moved. And that kind of solution is going to be a solution for any moment that the thing starts to move. So you can tell me that the ball stays there over time for a certain amount of time, and then at some moment that you pick, completely arbitrarily, it starts to roll. That is a solution to Newton's equations of motion. And furthermore, there are backward solutions, right? The laws of physics are time reversal invariant. So there are solutions where the ball rolls up and it slows down and then it gets to the top and it stays there forever, okay? So in both of these cases, you can't predict the future from the past. And so just to be super duper clear here, when the ball rolls up to the top and sits there, it doesn't roll up and go slower and slower and slower. It's not like Zeno's paradox, that it sort of gradually asymptotes to the top. It reaches exactly the top at some finite time, and then it stays there forever. Or it stays there for some time and then rolls down in a different direction, right? All of those are solutions to Newton's equations. And it has to do with the fact that these equations are nonlinear in particular ways. But the point is that given strictly the construal of classical mechanics defined by Newton's equations, there is not perfect determinism in there. That's not quite how the equations work out. Now, it's obvious from this example, or it should be obvious, that you really do need infinite precision to set up these initial conditions. The technical term is it's a set of measure 0 in the initial condition space, so it's never going to happen in the real world, but it could happen in principle, right? So that's the kind of thing that philosophers and mathematicians care a lot about. In principle, it could happen. So you can't say that even good old Newtonian Laplacian physics is perfectly deterministic in that sense. However, having said that, I said that both because it's intrinsically cool and because, you should know what the limitations are when you say something like Newtonian mechanics is deterministic. I say it all the time because what you really mean is it's deterministic up to, except for, a set of initial conditions of measure 0, okay? But maybe that's interesting. Of course, we know that Newtonian mechanics is not right. Quantum mechanics is right. So the question will be even more complicated once we get into quantum mechanics. Okay, so you could imagine saying, well, then even in Newtonian mechanics, you can imagine that things will happen in the future that cannot be strictly predicted from the past. And that's true more broadly, that we have situations where you can't predict exactly what's going to happen. But things like this, things like Nortons Dome, are not the real reason why we have that kind of unpredictability in nature. In the real world, we have unpredictability, when we go gambling, okay? We have Las Vegas behind me here. And this was, in fact, historically, this played a big role in the development of the theory of probability. I think that my understanding is, as with many things in math, the initial steps were taken during the Islamic Golden Age, right? Arabic and Persian mathematicians worked out some probability tables. A lot more progress was made in the European Enlightenment and the scientific revolution. People like Fermat and Pascal were literally worried about playing dice and playing cards. And that's how they worked out a lot of the theory of probability. Our old friend Pierre-Simon Laplace worked out some of the important issues in probability. Actually, John von Neumann, I think I mentioned, I might have mentioned, it appeared on the podcast I did recently, on the Mindscape podcast with Maria Konnikova, where we talked about poker and poker theory. And a lot of game theory, as we currently understand it, was invented by John von Neumann because he wanted to become a better poker player. So the real world aspects of probability come up in gambling and in games of chance, and that leads to a mathematical formalization of it. So we want to understand how you can have these issues of probability, like you don't know whether the coin is going to turn up heads or tails, right? You say the coin has a 50-50 chance of being heads or tails. There are 52 cards in a deck, half of them are red, half of them are black. You say the chance of getting a red card as the next one flipped over is 50%. Things like that. What does that mean in a world that in principle is governed by Newtonian mechanics? It's not this, right? So I mentioned Nortons Dome as an example of the very, very delicate but precise ways in which Newtonian physics is not quite deterministic, but don't leave behind the fact that mostly it is deterministic, okay? Like Nortons Dome and similar kind of counterexamples are not what's going on to lead to questions like the coin is 50-50. What's going on is that we don't know what the exact Laplacian initial conditions are. We do not know what the position and velocity of every molecule in our bodies or in the coin or in the deck of cards are. So we want to formalize that into a notion of probability. So, oops, we're green here, sorry. So we want to talk about what it means to be probability, and that sort of has two aspects. One aspect is the sort of the formal mathematical aspect. How do you define probability and put it to work? But then there's the more philosophical aspect. What do you mean by probability? And both of these, I was going to say both these are complicated, but they're complicated in different ways. The mathematical way is just, it's figured out. We basically know the aspects of probability that matter in simple cases. There's some definitions, etc. you have to remember. The philosophical underpinnings are still under debate, actually. People disagree, and they disagree in very practical ways that have consequences for how we do science. So it's worth thinking about that. But let's do the math first, okay? Let's do the sort of the mathematical formal aspects. We define what we mean by probability, okay? So we say that, here's the picture we have in mind. We have a universe, U, of possible events. So we have a universe of events, and let's call the events X, Y, Z, etc. So here are some events. It's just a set. This is, don't, think of this blob as representing anything particular. It's just a collection of possible things. So the universe might be the universe of possible outcomes for tossing a coin. It might only have two events in it, heads or tails. It might be the universe of possible cards you can draw from a deck, and then it would have 52 different events in it. So here's events, X, Y, etc. And then there are subsets. We can group them into subsets of events, A, B, etc. And the subsets may or may not overlap. So, here's a subset A, here's a subset B, they overlap. And what we do is we define a measure on this space of events. So a measure is a way of assigning sizes to different subsets of some bigger set. So I've already used the term measure zero when we were talking about the set of initial conditions that lead to Nortons Dome. There's zero measure. They exist, these initial conditions, but they're of zero measure. You would never hit one randomly if you were choosing initial conditions randomly out of a bag. And so we want to define a probability measure. And the way to do this was formalized by a mathematician, Kolmogorov. So we have the Kolmogorov axioms for probability. And they're actually pretty simple to state. Well, I'm not, there are different levels of complexity and rigor you can state them at, so I'm going to be a little bit casual here. Like when you have infinitely big or continuous sets of possible events, then things get complicated. But with finite sets, it's pretty straightforward. So one axiom is that the probability of any event is always greater than or equal to 0. Okay, the probability measure is never negative. The probability for something is not negative. Now, as soon as you say that, some mathematician in the back of the room starts thinking, I wonder if I can define probabilities with negative values. Of course you can. You can define non-standard versions of probability. The Kolmogorov axiom say probability is never negative. The total probability, so if you add up over all x's in the set that you're considering, the probabilities of those x's, you will always equal exactly 1. So the probability of something happening is exactly 1. Okay, we accept that, right? That seems reasonable for a definition of probability. And finally, slightly more non-trivially, but still pretty easy to understand, if you have two subsets, A and B, that don't intersect. So that's math notation. A intersection B is the empty set, okay? So this is not true for the subsets I drew here, but you could imagine two subsets that don't intersect. Then the probability of being in the union of A and B, okay, the probability of being in either A or B, so you could write that as the probability of A union B, equals the probability of A plus the probability of B. Now I'm saying here the word probability because that's what we're going to put this to use for, but this is just math, okay? We don't have any interpretation necessarily that we attach to what this is. This will work for probability, but mathematicians just think, well, yeah, this is a measure that I can define on a set, and it has certain formal properties, and I can manipulate it, okay? So at that level, there's a lot you can do just from these very simple axioms. I'm not going to do anything complicated here, but I'm going to give you some lingo that we might find useful later. So you can define the joint probability. One of the things about this whole subject of probability and statistics is that it is so useful that many different subfields use it, right? Obviously, physicists use probability all the time. Pure mathematicians use it. Applied statisticians use it. Other kinds of scientists use it. Information theory, computer science, they all use it. And they all have developed slightly different notations for doing so. So the probability notation that you might be most familiar with, depending on what you've seen, might be a little bit different than what someone else uses. So I gotta use what I'm used to using. You'll go along with me, right? So the joint probability is what in my field we write as A comma B. And this is basically the probability of an event being in both A and B. So when you write P of A, that's the probability that the event that you randomly choose from the universe happens to be in A. When you write P A comma B, that's the probability that when you randomly choose an event, it is in both A and B. So it's in that intersection right there, right? So the probability of being in A and B is equal to the probability of being in the intersection of A and B. That's what we call the joint probability. And there's also something we can call the conditional probability. And the conditional probability is written PA bar B, and you can read this off as either the conditional probability of A given B or just the probability of A given B. It's the probability that if you know the element, the random event, is in the subset B, what's the probability it's also in A, okay? So that's just the probability that the event is in both A and B, so that's the joint probability we already just mentioned, divided by the probability it's in B to start with. So this is saying, given that you know you're in B, what is the probability you're also in A? Okay, so it's the probability that you happen to be in both of them, full stop, divided by the probability you were in B in the first place. And so this is very, very useful when you do inference, when you do statistical inference, saying, oh, I know one thing is true, what's the probability something else is also going to be true? If you're playing poker, you're playing Texas Hold'em, and you have two cards in your hand, you have one ace. You might want to say, all right, there's 6 other people at the table. What is the probability that one of them also has an ace or 2 aces or something like that, given that you have an ace? That's a conditional probability. So you can see why gamblers are going to be very interested in these this formalization of probability. Okay. But this is what you need to do math of probability. You can define a whole bunch of more things. There's mutual informations and entropies and things like that you can define for these probability distributions. But then you can also ask, okay, given that this is the mathematical formalization, what is probability physically? Where does it come from? What does probability mean? And that's much dicier. It's not that we don't know the answer. Well, we don't know the answer. It's not that we don't have an answer. It's that we have more than one possible answer, and people don't agree on what the right answer is. Probably, as is often the case, it's not that there is a right answer. It's that in different circumstances, different answers are appropriate. Okay, that's not going to stop people from arguing. So there are two notions of probability that get a lot of play, and maybe this is the exhaustive set. Like, I'm not an expert in the philosophy of probability, so I'm trying to give you the very basics here, not the comprehensive once and for all viewpoint. There's something that you might call objective probability. And objective probabilities are sometimes called chances or propensities. These are not exactly the same thing, but I'm not going to tell you what the subtle differences are between them. I'm just letting you know the vocabulary words. So if you thought, for example, that in quantum mechanics, the probability that uranium atom will decay in a certain time, okay, you could easily imagine, I'm not going to say, again, what's right or wrong, but you could imagine it being the case that that's just an objective fact about the world, right? Given a certain time scale, given a certain isotope of uranium, what is the probability the nucleus will decay? That's just a fact about the world, okay? It's not up to you. It has nothing to do with what you know and what you don't know. It's just a fact. So that viewpoint would go. So we call that the chance that this is going to happen. And there's a view of probability that things have a propensity for happening, and therefore they get this objective probability out of that. I'm not going to go into those details, but these are the words that are attached to that. And this point of view that probabilities are objective things about the world goes hand in hand with something called frequentism. And frequentism is the idea that you should define a probability by imagining you can do something an infinite number of times. So when someone says, what do you mean when you tell me that the chance that the coin flip is going to give me heads is 50%? A frequentist would say, well, what that means is if I flipped the coin an infinite number of times, I would get 50-50 heads and tails. That's what it means to say the probability. And furthermore, I mean, there'd be a footnote there saying, and there's nothing else I can tell you about the structure. It's not that the coin flips it's not that it gets tails every time heads was the last one, like it alternates heads, tails, heads, tails, heads, tails. That's not quite what they have in mind, because then there's something extra you could say that would give you additional information. If all you can say is that if you flip the coin an infinite number of times, you get 50-50 heads and tails, that's when you would say there's an objective probability of getting of heads being 0.5 or 50%, right? Okay, so that's an idea. There are obviously advantages to this idea, this notion of probability. Anytime something can be objective, that's good, right? We like it when it's objective. The opposite of objective is subjective, or the contrasting idea. And subjective means relative to a person, right? A subjective thing, the subject, the self, the I, right? It gets all very philosophical. So objective is just out there in the world. Everyone agrees. Subjective is somehow more personal. And it's nice when things are objective. I mean, that makes them sound like it's science. It's not just my feelings that are involved, right? But on the other hand, the idea that you define probability by imagining you're able to do something an infinite number of times can be a little bit impractical, right? Like you never actually do anything an infinite number of times. And some things you know perfectly well are only going to happen once. Like in my book, Something Deeply Hidden, when I talk about quantum mechanics, I talk a little bit about subjective versus objective probabilities. And I use the example of the 2020 NBA championship. And I say that there is a probability that the Philadelphia 76ers are going to win the 2020 NBA championship. Now, that only happens once, right? But we talk about the probability. We bet on it. You can gamble on probabilities like that. Now, ironically, I didn't know at the time there was a chance that nobody would win the 2020 NBA championship because of quarantine. It looks like it is going to happen as of this recording that I'm doing right now. But still, the point being that there are things that clearly are subjective, and yet we use probability talk about. And for that matter, we couldn't even imagine what it would mean to be a frequentist about something like that. if you think it's possible to talk about probabilities of one-time events like the 2020 NBA championship, you clearly can't mean the frequency of it happening an infinite number of times, because you can't do that experiment an infinite number of times. The basketball players would get older. You'd not be doing the same NBA championship over and over again, okay? So you mean something else when you say the probability of that event in the future is a certain amount. And what you mean is typically taken to be the credence. I don't know. So I started thinking in the middle of writing there once again. Always a bad idea. Credences, to be plural, just like there, that's your subjective degree of belief, right? The degree that, the amount you'd be willing to bet that something was going to happen. And this, just to drive home that it's not just a frequency, you can have credences about events that already happened, right? What is the credence that only one shooter shot JFK, right? People disagree about whether or not that's true. There is an answer. I mean, you think there's only one answer to it, but if you don't know it, if you have some ignorance, then you attach a credence. You say, well, I think there's a certain probability that that was the case, a certain probability that it didn't happen. So this comes from ignorance. And not ignorance in a pejorative sense. There's something you should know and don't. Something you just don't know. Like many things about the world you don't know. No person is Laplace's demon who knows everything. So we talk about probabilities in these two different ways, and you might want to know, well, which is right, or which should we use? And I think the answer is, I'm not sure what the answer is. Let me put it this way. I think it's absolutely necessary to use subjective, credence-like probabilities in some cases. Like I just said, for the NBA championship or for Kennedy's assassination or whatever, it makes perfect sense to talk in the language of probability, and it's clearly not a frequency. It's clearly not even objective. People can disagree. I'm less clear about whether there's anything in physics or in science that can really be called an objective probability, but maybe there is. You could certainly imagine a world in which it is. We talked earlier about the GRW theory of quantum mechanics, right? The objective collapse model, when there's a probability per unit time that the wave function of the electron just localizes onto some point. If that theory is right, there is some objective chanciness to the universe, and then it would be very clear that you could use that kind of frequentist approach to define what you mean by probability. What we can do is, if you think that there are objective frequencies, you can also admit there are sometimes objective probabilities. There are also sometimes subjective probabilities, credences, and then you can talk about trying to relate the two of them to each other. So David Lewis, who's a famous philosopher, he's extremely famous among other philosophers. He's less famous among the general public. But he invented what is called the principle. And I know that the name is a joke. That was intentional. But he called it that. So principle. Always a 50-50 probability that we'll get the right spelling first and later. Principle. So the most important principle, right? And the principle, the jokey name, says that when there are, I'm not going to write the whole thing down, when there are objective chancy kinds of probabilities in the world, and you have subjective credences that you're going to assign to these different outcomes, you should align your credences to the objective chances. That's what the principle says. Your credences are personal, they're subjective, you can pick them, you can say, I don't believe that this is true, but Lewis is saying when there are objective facts about the frequency of something happening, you better, if you're smart, as a normative guideline, you better align your credences to the chances, whatever they may be. So this is, again, a philosophical can of worms. It seems very useful, but I'm not going to go into the details. I just want to let you know that you can live in a world where you believe in both objective probabilities and subjective ones, and they can happily play along under the right circumstances. Okay. That was both a little bit of the math background, what probability is, how we talk about it, a little bit of the philosophy background, what it means. Now we can put it to work in physics, okay? That's what we're really here for. So in physics, where probability really came into the game was in the 19th century. The 19th century is underrated in the history of physics. We talk about ancient physics with Aristotle, then we talk about like Galileo and Newton, and sometimes if you give a very quick history of physics, you tend to skip from Galileo and Newton right to Einstein and quantum mechanics. But then in the 1800s, the 19th century was just chock full of cool stuff with statistical mechanics, which we're going to talk about here, electromagnetism, the precursors to special relativity, atomic theory, lots of cool stuff. So we're going to think about statistical mechanics in a very simple-minded way. That is to say, let's think about a box of gas. This is the standard example that we all like to use. Let me see if my pen will do this. Make a square. There we go. That's a box. Make it a little bit more square. And then we're going to fill it with gas. And we know, because we are modern physicists and we've had the last couple of biggest ideas videos, we know that there are really atoms in the box of gas, but we also know that none of us knows exactly the positions and velocities of all the atoms. So we talk about the atoms as a gas instead, with certain coarse macroscopic properties. So how do we relate the fact that we think that really there is a single description of the positions and velocities of all the molecules to the fact that we don't know what that is and we still hope to do some useful physics with it, okay? So let's define a few notions here. So we have the phase space for a single particle, right? Which we would call one particle phase space. That's the information you need to give me to say what's going to happen to one particle. If you knew what was happening to all the other ones, you need to give me the position and velocity of this particle, and then all the forces acting on it. So that is the position and the velocity of that particle. Remember, when we talk about phase space, we can move back and forth from velocity to momentum. This is all not relativistic, so we're just doing Newtonian mechanics. Momentum is m times the velocity, so they're interchangeable. And this is six-dimensional. Okay, 3 velocities, 3 positions. We're in a 3-dimensional space. I've only drawn a 2-dimensional box, but you know what I mean. And this is called, for reasons which will become only slightly more clear in a second, mu space. So we have a lot of particles in the box, but for any one of them, its phase space is a 6-dimensional space, and we call that mu space. We could also talk about the phase space of the entire system, right? So that also has a phase space. Every physical system has a phase space that describes it. So if you have n particles, the n particle phase space is a whole set of things, right? x1, v1 for particle 1, comma, x2, v2 for particle 2, and then maybe a lot of them. You could have Avogadro's number, 10 to the 23, or many, many more particles than that. And this is 6n dimensional, because there's 6 dimensions for each particle, its phase space. And this is called gamma space. So I actually do not know why mu and gamma are the 2 letters that are used for these 2 different ideas, but at least it's clear you need 2 different letters, because these are 2 different things, right? The phase space for the whole thing is gamma space. The phase space for just any one particle at a time is mu space. And the reason why we're distinguishing between these is because you might think that the sensible thing to do is to go into gamma space, the phase space for the entire system, and have some probability distribution on that space and see, ask what you can do with the physics of that probability distribution. And it's true, you might want to do that, but it turns out to be hard, so actually people work in mu space, which is much simpler because it's only 6-dimensional. So one point in gamma is the same as n points in mu. So in other words, you can think of the phase space description of this n particle system as a single point in a big 6n dimensional space, or as a cloud of n points all living in the 6-dimensional space. That is completely mathematically equivalent, okay? It's all about what is more convenient for the problem that you're going to do. So then you say, okay, well, I have an actual box of gas. Let's do the following weird thought experiment. Someone comes into your room where you're sitting, and they hand you a box, and they say, there are n particles in the box. Maybe you can even weigh the box, and you can say, okay, I know exactly how much energy is in the box. But that's all you know. Okay, you know the total energy in the box, you know the total number of particles. Remember the energy per particle, the energies are just going to be the kinetic energy, this is particle I, is 1/2, and let's imagine they're, just for simplicity, particles of equal mass, okay? So they're hydrogen atoms or something like that, 1/2 mvi squared, just the kinetic energy. So we're ignoring the gravitational potential energy, or we're ignoring interactions. Maybe the particles can bump into each other, but they don't have long-range forces acting on them. So there's no potential energy or anything like that. And if you imagine that, okay, that's all you know, is that there's a certain amount of energy in a certain number of particles, maybe, so what could you do? You could maybe say, well, I could be indifferent. So there's another principle called the principle of indifference, which is one of those things where in different circumstances we'll have different definitions, etc. But basically it says when you have a bunch of possibilities and there's sort of a symmetry between them, okay? There's nothing special that says some possibilities are different than others, then you assign them equal probability. That's the principle of indifference. Equal probability to similar circumstances. So, for example, you could imagine describing the box of gas in gamma space by one point in gamma space. Now, some of these points will have different energies than others because the velocities are different. So there's some submanifold of gamma space of constant energy where, the total energy, this is per particle, EI, E total is the sum over I of 1/2 mvi squared. So if you think about it, if you fix E total in velocity space, this is a sum of squares. So you're saying the sum of squares equals a constant, which is picking out a sphere. There's a spherical region, the surface of a sphere in velocity space. So on that sphere, on that submanifold of fixed total energy, the principle of indifference would say, give me equal probability to be in any state. Any positions, any velocities that are compatible with that total energy, give that equal probability. And sometimes people do this. This is called the microcanonical ensemble. I never remember what the names of various ensembles are. But that's one thing that you can do, and you can make progress that way. But it's a weird thing in some sense. I mean, who is this person who walked into your room handing you a box of gas? And how do you know they aren't tricking you, right? Like, how do you know what they did to prepare the gas in the box? Like, they could easily make it so that all the molecules are moving to the left, right? And they hit the wall and they all move to the right. That would not at all be compatible with the principle of indifference. That's a very, very specific kind of thing. So the principle of indifference, it has a long, complicated history. I think Laplace was one of the people who talked about it. I'm not sure he actually completely advocated it, although he often gets credit for saying it, the principle of indifference. But, it's a sensible thing to do probably if you don't know any better, but maybe sometimes we know better. So there is a situation in which we can do a little bit better. And that is, let's instead of this, instead of someone just handing you a box, let's imagine we have a box, but it's a slightly more real-world box in that the edges of the box are relatively thin, and the box is sitting in a room with some temperature. In other words, there can be a little bit of exchange of energy between the box and the room. So particles cannot leave the box. They're stuck in the box. The number of particles is fixed. But there are air molecules outside that are bumping into the sides of the box. And the particles inside the box are also bumping into the edges. So there can be slight variations in energy exchanging between inside and outside. So we imagine that the box is basically embedded in a heat bath. You don't maybe sometimes think of the air in your room as a heat bath, but that's what it is. So again, box of gas, particles, and outside there's stuff at temperature T that can gradually interact with what's going on inside the box. So what's going on inside the box is not completely a closed system. It can exchange energy a little bit, but the number of particles is fixed. And you're not looking inside. You're not seeing what's going on inside the box, okay? So that's how we're going to physically change the situation a little bit. We're also going to change mathematically how we deal with it a little bit because this gamma space thing, this 6 n-dimensional phase space is just too big. So rather than working with a probability distribution in the n-dimensional, 6n-dimensional gamma space, the n-particle phase space, we will work with what's called a distribution function in mu space, in the one-particle phase space. So this is a bad name, distribution function, because different subfields use the same terminology and mean very different things. But this is how physicists use it. The distribution function f as a function of x and v, so it's a function in mu space, so just in the one particle phase space. And what it tells you is the density of particles on average in that region of phase space. So remember, in mu space, you can think of the whole collection as a cloud of n particles, and n is really big, 10 to the 23 or bigger than that. So it's almost like a smooth cloud, right? It's really a discrete set of points, but you can approximate it, and this is what you're doing here, as a smooth function in phase space. So if you really simplify your life by looking just at two dimensions here, x and v, then you have some point, some little tiny region in phase space, and f of x and v is the average number of particles in that region. So, but it's important that it's in phase space, not in space. So F is not the density of particles in physical space in a little cubic centimeter. It's the density of particles in phase space. So both particles at that point, at that location, with this velocity, a velocity in a certain direction. Okay. Now this is throwing away some information already, right? There might be correlations or relationships between the particles, even if they're at similar points in phase space, that this formalism does not keep track of. Still, that's what we do. This goes back to people like Maxwell and Thomson and Boltzmann and stuff like that in the 1800s. They decided to simplify their lives by working in the one-particle phase space instead of the n-particle phase space. And I should say that just to normalize things, this is not really a probability. We told you that when you add up all the probabilities of everything, you always get 1. This is a number, a distribution function, so it's related to the total number of particles by saying that the integral of f, which is a function of x and v, over d3x, d3v, is not 1, but the number of particles. So you can have a lot of particles in some little region of phase space, less in some other region. And then what you're able to show, what you're able to do physically, remember we've embedded our box in a heat bath, so you say what happens, and what happens is, physically, the gas will approach an equilibrium distribution. And the equilibrium distribution, we actually know what it looks like. It's named after Maxwell and Boltzmann. Be embarrassing to misspell Boltzmann. Maxwell-Boltzmann distribution. So this is an astonishing, wonderful fact about statistical mechanics. This is, precursor to all the talk about second law of thermodynamics, which we'll eventually get into in a later video. But this simple arrangement where someone gives you a box of gas, it doesn't matter how they arranged it. It doesn't matter how they started. You let a little bit of heat exchange happen across the boundaries of the box, and what happens is that no matter what the initial conditions were, the probability distribution function, inside the box approaches a Maxwell-Boltzmann distribution. I'm going to tell you what that is. What is it? So the Maxwell-Boltzmann distribution is a particular form of the distribution function f of x and v. So it's going to be some function of x and v, the positions and the velocities. And what function is going to be? Well, remember, we're ignoring gravity, right? So it's not like there's more density near the bottom of the box than up there in the box. What this means effectively is that the random motions, the temperature, are more important than the fact that gravity wants to pull things down, okay? So what that means is that the Maxwell-Boltzmann distribution is going to be smooth. It's going to be invariant under, what is the word that I wrote down? Spatially uniform. That's what it's going to be. There's no reason to have it be more probable to find a particle over here than over there, right? It's going to be the same probability at every point in space. So what that means is that f of x and v is actually just a function of v. It's not a function of x at all, okay? There's no difference in probability from one point to the other. It's also rotationally invariant, or isotropic, if you want to say that. So we have a function that is just a function of velocity, but velocity is a vector. It has a direction as well as a magnitude. And what this is saying is that there's no preferred direction in the box. You know, the shape of the box, whether it's really a cube or anything like that, doesn't really matter. Particles are all bumping into each other, and they're bumping into the sides. And what that means is that this function of v is actually just a function of the magnitude of v. V equals the magnitude. It's the same in every direction, okay? Finally, okay, so there's some function of v that is the Maxwell-Boltzmann distribution, and I'm just going to tell you what it is. F of v, well, there's some prefactors I'm going to ignore, so it's proportional to v squared times e to the minus 1/2 mv squared, which you'll recognize is the energy of that particular configuration, of that particular particle, divided by kT, where T is the temperature. Remember, we've embedded our box in a heat bath with temperature T, and K is a constant of nature called Boltzmann's constant. I'm not going to tell you what that is either because we set it equal to 1. And just like h bar and c, we will end up setting k, Boltzmann's constant, equal to 1. We'll try to remember it. Okay, so what this is telling us is that if we plot this very specific functional form, here's f and here's v, well, there's two things going on. One thing is that there is a v squared, so that's a parabola. It looks like this. The other is there's e to the minus v squared, roughly speaking. So 1/2 mv squared is the kinetic energy of a single particle, and it exponentially decreases as that energy goes up. So if I plot e to the minus 1/2 mv squared on this plot, it looks like this. And I multiply these two things together to get the Maxwell-Boltzmann distribution, and it looks like this. It goes up, has a peak, then it's going to go down again. So this is the Maxwell-Boltzmann distribution. It has a peak at some particular velocity. And what it's saying is that you can find this is saying what is the density of number of particles in phase space, right? So what is the number of particles with this particular velocity? What's the number of particles with zero velocity? Well, it's small, okay? It approaches zero as you go to zero velocity, but only because there's only one way to have zero velocity. There's a lot of ways to have a little velocity. And if you're thinking about small velocities, much, much smaller than kT, then the e to the minus 1/2 mv squared doesn't matter. It's almost a constant. It's approximately constant compared to the v squared, which is growing. And what it's basically saying is that there's just more ways to have a large velocity than a small velocity if the energies are not that different from each other, okay? That's where the v squared comes from. Remember, we said up here, constant energy is like a sphere in velocity space. So the reason why it's v squared is because the area of that sphere goes like v squared, right? Areas go like distance squared. But then what this is saying is that given that you're exchanging energy with your environment, probably the typical energy of a particle in the box is going to be the same as the temperature outside. And it's possible for a particle inside the box to have a much larger energy than that, but it becomes really, really unlikely. It becomes exponentially unlikely. This is e to the minus the kinetic energy in units of kT, in units of the temperature outside. So that's the Maxwell-Boltzmann distribution. And it's an amazing fact of physics that a box of gas embedded in a heat bath approaches this distribution. And this idea of embedding in a heat bath like this, if this is the microcanonical ensemble, which says completely equal probability given a fixed energy, here the energy is not fixed, right? Because it's exchanging energy with the environment, and you get what is just called the canonical ensemble. The temperature is kind of like the average energy, but there are fluctuations around that, okay? So this is what you reach in the canonical ensemble. And why? How do you derive this? Well, there's different ways to derive this fact. One way is this is the maximum entropy configuration that the gas can go into, given that it's going to be at this temperature, okay? Given you have a number of particles and there's going to be a temperature it's going to reach, this is the maximum entropy configuration. So the entropy, we're not going to go into this in detail right now, but the entropy is something you can also define given this distribution function. There's a formula for it. And the formula is S equals minus the integral of f as a function of x and v. I'm not going to draw all the little vector signs here, times the log of f of x and v, d3x, d3v, okay? I think I told you about logarithms before, right? So if you have the e to the logarithm of x is equal to x, or likewise, the logarithm of e to the x equals x. That's what logarithm means. So this formula minus the integral of f log f, that's the entropy. That's one of the ways in which you could talk about entropy. You could also describe it in terms of gamma space. This is mu space that we're in right now, but this is a nice little thing that you can define. It's a finite number. Boltzmann showed, I think it was Boltzmann who showed, I think Maxwell guessed or argued his way into the form of the Maxwell-Boltzmann distribution, and then Boltzmann did some more rigorous investigation of it. But it maximizes the entropy. And as we'll talk about later, that's a way of saying that given the constraints, given the fact that there's a certain number of particles, given the fact that the temperature is a certain value, and the temperature is the average kinetic energy, etc., most of the allowed phase space is in this maximum entropy situation. That's why you tend to go to the Maxwell-Boltzmann distribution, because most particles will look like that under this condition. So this is a wonderful example of statistical mechanics. The idea that really it's not, this is absolutely an example of the subjective probability in action, okay? Because we all think that in that box of gas, we all would have thought in the 1800s, when Maxwell and Boltzmann were talking about this, that there were atoms or there were molecules and they had some particular positions and velocities, but we don't know what they are. And so we can assign credences, we can assign probabilities to the different possible ways you could configure the points in phase space, and Maxwell-Boltzmann say, well, this is the particular distribution that we should end up getting by maximizing the entropy. And it's that kind of thinking that helped them invent this whole field of statistical mechanics. Again, Maxwell-Boltzmann, also Gibbs, Thomson, aka Lord Kelvin, and their friends, set up this whole formalism of statistical mechanics. And it's amazing. So what it's telling you is that you can do physics, you can learn things. We learned something. We said, what happened to a box of gas? That's a very physical, tangible, measurable, observable thing, even without knowing everything there is to know. So this is crucially important to mapping this microscopic physics, whether it's deterministic or not, onto the macroscopic world. Can you still say something about the macroscopic world, even if you don't know everything about the microscopic goings-on? And this is the first indication that, yes, you can, and you can sort of quantify your ignorance and nevertheless say interesting things. And so statistical, it was very controversial at the time. Back in Germany, people were very slow to catch on to statistical mechanics, and Boltzmann in particular got a lot of flack from a lot of people because he was in Germany. Like the British caught on to it pretty quickly, so Maxwell and Thomson were fine. They were celebrated, and Boltzmann had fun with them. But then when he went back to Germany, he got a lot of flack because a lot of people in Germany, led by Ernst Mach of Mach's principle fame, didn't want to believe in the existence of atoms. Okay, they thought that things like the second law of thermodynamics were not probabilistic laws that you get from averaging over lots of atoms. That they thought there was some law of nature that said entropy increased. So, but the statistical point of view won out in the end, and it's a wonderful example of the use of probability in physics. So that was the 19th century. Okay, so the lesson is we can use notions of probability because we're ignorant, because there's something we don't know about the system. Then the 20th century comes along, okay, and we have quantum mechanics, and that seems to be a whole other kettle of fish. As you know by now, quantum mechanics tells us that when we measure an observable feature of a quantum system, you cannot predict what outcome you're going to get with perfect certainty. The best you can do is to predict a probability, or to state a probability of getting different experimental outcomes. That seems different. You have the Born rule, that the probability of getting some outcome x is the wave function that we associate with x, magnitude squared. And it seems, certainly in the well, I almost said certainly in the Copenhagen interpretation, but the phrase certainly in the Copenhagen interpretation should almost never be used because the Copenhagen interpretation is not very well defined. But certainly in the minds of many people, this kind of probability, which you'll notice does fit all of Kolmogorov's axioms there, okay? It fits very well, as long as the set of events that you're allowed to look at are compatible with each other. So you cannot observe position and velocity at the same time. But if you look at the probability for all the positions of an electron, for example, they would satisfy Kolmogorov's axioms. By the way, again, parenthetically, what you could do, rather than what I just did, which is to brush under the rug, the fact that you shouldn't think of observing position and observing velocities or momentum at the same time when you talk about the probability in quantum mechanics, you can instead try to develop a quantum mechanical theory of probability, which is different than Kolmogorov's theory of probability, and that's another way you can go. But as long as you just pay careful attention to what you're allowed to observe at any one time, ordinary probability works perfectly well. Okay. But it seems like an objective feature of the world. So this is supposed to be the point of something like Bell's theorem, right? The difficulty of finding hidden variables, at least local hidden variables, is that the reason why there's only a probability we can attach to different outcomes isn't because there's some thing, some fact, some values of some parameters that we just don't know. It's because they are intrinsically unpredictable, okay? But then other people, Bohm will come along and say, but well, I can invent a theory that says that there are hidden variables, and Everett comes along and says something completely different. So it's subtle, and actually the answer is in quantum mechanics, given that we don't know the once and for all true theory of quantum mechanics, that means we don't know what probability comes from in quantum mechanics yet. Different schools of thought think they know, but they don't agree with each other. So let's contrast three popular approaches to probability in quantum mechanics. And these are just the three approaches to quantum mechanics that we talked about before. So one would be hidden variables. So the hidden variable theories, like Bohm's, say that in addition to the wave function, there are some other variables, like positions of particles, and you don't know what they are. And in fact, there's an argument that they should be distributed according to some equilibrium distribution. And then you can sort of argue about that argument, but that's a big part of being a good Bohmian. And then you use that equilibrium distribution to derive that you get the Born rule for actual experiments. So in hidden variable theories, you have psi plus, let's say, particle positions, both the wave functions and these extra variables, and these particle positions are unknown. So it is exactly like statistical mechanics. It's perfectly deterministic. There are equations for how psi evolves and for how the particles evolve. So let's make that very clear. The Schrödinger equation, H psi equals I d psi dt, okay, this equation is 100% deterministic. It is more deterministic than Newton's laws. Remember, that was the point of telling you about Nortons Dome. F equals ma looks deterministic, but there are these sneaky little exceptions to that. The Schrödinger equation is linear, which is a way of saying that on both sides of the Schrödinger equation, psi, the wave function, appears exactly once. It's not psi squared or e to the psi or anything like that. So the kinds of sneaky set of measure zero non-deterministic behavior that exist in Newton's laws are not anywhere to be found in the Schrödinger equation. Given the Schrödinger equation, it is true that I can evolve it forward and backward in time. The reason why we get the Born rule is, of course, because quantum measurements don't obey the Schrödinger equation. Something else seems to be going on. And in hidden variable theories, in addition to the Schrödinger equation, you also have a guidance equation. That's why hidden variable theories are sometimes called pilot wave theories. You can think about the wave function as a wave that pushes around the particles, but the guidance equation is also completely deterministic. The indeterminism comes in because you don't know the positions of the particles, just like in statistical mechanics. So this is an example of subjective probability. So, oops, that was terrible. Oh my goodness. Subjective probability. because you don't know the state of the system. There you go. But in contrast with that, like I already mentioned, you have GRW/objective collapse models, which just say, as part of the postulates of the theory, that there's a certain probability per unit time that the wave function is going to collapse. Okay, that's what objective collapse means. The original GRW theory is just truly random in that sense. There's other theories like Penrose's where the collapses are triggered by something. Some physical event makes collapse happen, but what the collapse is actually to is still completely random. So these theories are objectively probabilistic. So these theories, in other words, there's an objective chanciness, stochasticity, randomness to the world. It's a very, very different kind of probability than appears in the hidden variable theories. And then, guess what? We have Everett/many worlds. The tension mounts. Which is it going to be? Is it going to be objective probability or subjective probability? So, of course, Everett's got to be difficult. It's got to be a little bit slightly more complicated. In Everett, as you know, the only equation is the Schrödinger equation, right? That's the fundamental equation. I just told you the Schrödinger equation is 100% deterministic. So the fundamental dynamics of the wave function of the universe in Everettian many worlds quantum mechanics is just deterministic. Full stop. But, as you also know, because we also talked about it, probabilities nevertheless arise, and they arise from what we called self-locating uncertainty. So imagine that you are on a branch of the wave function here, and you have some spin, and it's in a superposition of spin up and spin down, and then you measure the spin, or let's say the spin gets measured, doesn't need to be you who does the measuring. And so there's a branch where the spin is up, and a branch where the spin is down, and that's going to happen faster than you know about it, okay? So the branching happens really, really, really fast. So there's a moment when there are two branches, and you don't know which branch you are on, okay? That's self-locating uncertainty. Sometimes called indexical uncertainty, because you'd imagine a little index that says, I am on this branch, but you don't know what the index is, okay? And so this is subjective uncertainty. It's something that you don't know, but it's a different kind of thing that you don't know, okay? Up here in the, oops, where'd it go? I lost my little, well, that's too bad. I lost my little highlighter. I don't know what happened. But anyway, up here, where we were in the hidden variable world, okay, there was something we didn't know, and the thing we didn't know was the state of the world. Right? We didn't know what the positions of the particles were, which is part of the specification of the state. In Everett, you can know the state of the world exactly, but there's still something you don't know, which is where you are in it. So that's a different kind of subjective uncertainty. You need to attach credences. That's something you need to do, but how to attach those credences is a little bit less obvious, okay? And I would argue, I have argued, other people have argued, that there is a clearly right, rational, sensible way to attach those credences, and that is to use the Born rule. The probability of being on any branch is the wave function squared. But other people don't quite agree with that. You know, they haven't yet seen the light yet. But what's interesting to me is that these pre-existing philosophical debates about the nature of probability and what it means are not only not resolved, but every possible option could be true, given what we know about quantum mechanics. If someone says, is the world fundamentally deterministic? We don't know. We don't know the answer to that. In GRW, it's not. In hidden variable theories and Everett, it is. There's other theories of quantum mechanics, obviously. So we don't know whether the world is fundamentally deterministic or not. If it is, how do probabilities arise in a deterministic world? We don't know that either. In hidden variable theories, they arise because there's something we don't know about the world. In Everett, they arise because there's something we don't know about where we are in the world. So it's interesting that none of this is yet settled. Again, I like to point out open problems for the youngsters in the audience to solve for their PhD theses. This is a good set of problems here. The relationship of probability and quantum mechanics, subjective and objective probabilities, and so forth. I should say also, remember I said before, I'm not even sure there are any objective probabilities in the world. So that goes along with me being an Everettian. This is saying that the probabilities that arise in quantum mechanics are subjective just as much as the probabilities that arise in statistical mechanics are. And David Lewis actually went even further than this. David Lewis, the same guy with the principal. His most famous thing is to talk about possible worlds. So he thought he understood, about Everettian quantum mechanics and so forth, but that was not his main focus. But he talked about the space of all conceivable, he said possible, I should say possible, all possible worlds. So there's by world, he doesn't mean a branch of the Everettian wave function. He means a set of laws of physics being instantiated in some universe, some reality, okay? So he's thinking of really different realities. I talk about this a little bit in podcast land, in Mindscape podcast. I have one podcast with Ned Hall, philosopher, and another one with Max Tegmark, a cosmologist, and we both talk about this idea of the set of all possible worlds, okay? So Lewis thought that there's a possible world which is Newtonian mechanics. There's a possible world where space is two-dimensional. There's all these different possible worlds, an infinite number of them. And Lewis thought about, how we should think about these possible worlds, and he actually thought they were all real. He advocated thinking of every possible world as really existing. You don't need to go that far. Modal realism, it was called, but you don't need to go that far. But he does point out that, we can think of all probabilities. Like, let's say, we don't know what the laws of physics are. We don't know what the dark matter is. Is the dark matter a weakly interacting massive particle? Is it an axion? Is it something else? Okay. Different people will assign probabilities. You have to like don't say you don't want to. Like if you're an honest, rational person, you should have credences for things. And maybe your credence is it's something else I don't know about. And maybe your credence is not very specific. But if you're a scientist, a cosmologist, you need to have credences. You need to, and the reason why is because you choose what to think about, right? You choose what to work on, how to spend your life. So if you think that it's very probable that the dark matter is a weakly interacting massive particle, then that means you have a high credence that that's true. If you think it's an axion or black holes or neutrinos, then you think that the credences are different. And so what Lewis says, at least once he said this, is that you can think of all probabilities, including the probability that the axions are the dark matter and so forth, the probability that a coin will turn up heads or tails, the probability that a certain radioactive atom will decay, can be thought of as self-locating uncertainties. Are self-locating uncertainties in the space of possible worlds. So Lewis says there's a possible world in which axions are the dark matter. There's a possible world in which weakly interacting massive particles are the dark matter. When you say, I think there's a 60% chance that weakly interacting massive particles are the dark matter, you're putting a credence on your self-locating uncertainty about which possible world you live in. So this is a different way of self-locating uncertainty to arise. In Everettian quantum mechanics, it arises because you don't know where you are in the actual world. Even though we say many worlds, it's still one big wave function of the universe. You just don't know where you are in that wave function. Lewis is saying you consider really different possible disjoint worlds. They didn't arise from the same world in the past through Schrödinger evolution or anything like that. They're truly different possibilities, and we don't know which one is true. So that's a kind of self-locating uncertainty, another way that probabilities arise. I don't know if this is actually true. I'm very sympathetic to it. I like it, but I don't understand it well enough to really say that I advocate for it. But I'm thinking about it. I think it's something that we should take seriously. Okay. Last thing I want to do in this video is to talk about how we decrease our uncertainty. So we have this uncertainty. We have self-locating uncertainty, for example. Anyway, we have probabilities. We have different theories of what is the dark matter, was there a Big Bang and stuff like this, different probabilities, what is the right theory of quantum mechanics? Is it pilot waves, hidden variables, GRW, Everett many worlds? We have different probabilities for this. And what we're going to do is science. We're going to go out there and observe things about the world and learn about it and hopefully figure out which of our probabilities are correct, right? So we're going to increase certain probabilities, decrease others. We're going to change our credences in different propositions by collecting data. And this is the whole universe of Bayesian inference. Honestly, it's amazing I've gotten this far in a video about probability and randomness without mentioning Bayes' name once yet. So Bayes' theorem is literally a theorem. It's not something that can be wrong. It's just if you have probabilities, probabilities obey a certain rule. In particular, this is saying the probability, how probability changes when you collect more data. That's what Bayes' theorem says. But you have to distinguish between Bayes' theorem and the whole bigger set of ideas called Bayesian inference. So let's first get to the theorem, okay? So imagine you have a set of mutually exclusive propositions, or let's call them theories, because this is very often used in the context of scientists trying to decide which theory is correct. But any mutually exclusive set of propositions works. The coin will become heads, the coin will become tails. Those are two theories, okay? So call them theories TI. One of them is the coin is heads, the coin will be tails. Those are two different theories. There's a prior in Bayesian reasoning, probability, for every theory. So this is P of TI. So this says even before you've looked at the world, before you've done any science, before you've done anything, before you've collected any data, before you flipped the coin, for example, you need to already assign a probability. You can't just say, no, I don't know. I don't know what it is. You need, in order to get along in the world, you need to be able to assign probabilities to things. So you start with a prior probability. The coin has not yet been flipped. Well, I'm going to give it 50-50 heads or tails. Those are my prior probabilities. And then I collect some data. And I'm going to call the data D. So maybe the data is, oh, someone just gave me a receipt for this person who's about to flip the coin had purchased a trick coin at a magic store that always turns out heads, right? So that's going to change my probabilities. I got some new data in there. Or, oh, a weakly interacting massive particle was just discovered at the xenon dark matter detector or something like that, okay? Data can come in various sorts. So what we do is we then define the likelihood of measuring that data if each individual theory were true, okay? So the likelihood is a conditional probability. The likelihood is saying, if this theory were true, if we conditionalize on that particular theory, then what would the probability have been that we would have collected that particular piece of information? We would have located that data. So the likelihood is the probability of collecting the data given the theory, okay? What we want to do is to update our priors with the fact that we've collected the data. So what we want is the posterior probability, the probability that our theory is true now that we've collected the data. So the likelihood is something we can calculate, right? Our theory should make a prediction. That's what it means. The theory predicts that the coin will be heads up 50% of the time or whatever. Different theories will make different predictions. And then this is what we calculate. So this is what we infer. So you calculate this, you collect the data, you start with this. Where do your priors come from? Yeah, don't ask me. This is the big looming question in Bayesian inference. You know, how do you choose your priors in the first place? How do you choose to think that weakly interacting massive particles are more likely than axions or whatever? You know, lots of different things go into it. You know, how pretty is it? How elegant is the theory? How simple? Have you written any papers on that particular model? And therefore, you'd be happy. You know, this is all stuff that could, in principle, go into determining your priors. And then you infer from all that after you've collected the data, what is your new probability for that theory? And so Bayes' law is how to do that. Bayes' law says the probability of the theory, now that you've collected the data, is equal to the probability that that you would have collected that data under the theory, times the prior for that theory, divided by the total probability that the data would be collected in some theory, okay? So the total probability of collecting the data is just the sum over all theories of the likelihood, probability of data in theory I, times the prior probability of theory I. So you can see that the thing on the top of Bayes' law is the thing we're summing over to get the bottom. So by construction, the left-hand side is going to be a collection of numbers between 0 and 1 that when you add them together, they're going to give you 1. Okay? Because when you add all the probabilities together, you're just taking the same thing on the top and bottom of this right-hand side of the equation. So this is guaranteed to give you a good probability. And this is every statistician's and many scientists' favorite rule. And so this is, again, this is a law, this is a theorem, this is how probabilities fit together, but it also suggests an attitude. It's just a mathematical expression, but it also suggests a philosophy of life. And the philosophy of life is there's a whole bunch of things that we're ignorant about. I mean, they may be true, they may not be true, but we should attach credences to them. We should attach priors. We should say, I think this is probably true, this thing is less likely to be true, etc. And then we should go through life collecting data and updating our priors using Bayes' theorem, just like this. And the sad fact is that people don't do this. This is you know, as someone said, people call this Bayesian rationality, but you might as well just call it rationality. It's just being rational about a world where you are not sure about things. Now, in fact, there's all sorts of psychological barriers to being a good Bayesian reasoner. There are examples where people are given data that is unlikely, according to their favorite theory, and they get defensive about it and become more and more wedded to their favorite theory. Okay, it's not doesn't always happen that way, but it's definitely something that can happen. It's hard to be a good Bayesian reasoner. Certainly, if you're playing poker, you should be a good Bayesian reasoner. I mean, you might say, well, I have 2 pair. I think that's the best hand. I will raise, and someone re-raises you. You should update. What is the chance that they would re-raise me? Well, it's low if they have a crappy hand, and it's high if they have a really good hand. So maybe I should lower the probability that my hand is the best one, right? You should be always doing Bayesian updating as you're sitting there playing poker. But it's hard to do in practice. Let's finish this up by running through one example of seeing how it actually works, okay? So let's use... it's just a modern physics thing that what we really care about is, what we're really annoyed by is this fact that we didn't discover any new particles at the Large Hadron Collider other than the Higgs boson, which we all suspected was there. We haven't discovered supersymmetry or extra dimensions or any of the other things we were looking for. So let's use that as an example. So here's an example. Let T1 be supersymmetry exists in nature. So T1, the theory 1 is that the fundamental laws of physics, whatever they are, have supersymmetry as an aspect. And T2 is that no, they don't. Supersymmetry is just a theorist's pipe dream. It is not part of the real laws of nature, okay? So imagine you're a physicist and you like supersymmetry. Imagine you're a physicist 20 years ago. You haven't yet turned on the Large Hadron Collider, and you have priors. So you've thought about it. You've thought about the mathematical elegance and the explanatory power and the unification prospects of supersymmetry, and you said, this all looks good to me. So you say, my prior on T1 is 0.9, and therefore my prior on T2, because these are mutually exclusive theories, and they're a comprehensive set. There's no third option. Supersymmetry exists or it doesn't, okay? So they better add up to 1, so I better give 0.1 for my prior. Nothing, this is just an illustrative example. You don't have to agree with this particular physicist, okay? We're just running the numbers. And then your data is we did not see supersymmetry at the LHC. We turned on Large Hadron Collider, we did not see supersymmetry. Now the way to play the game is, before you turned on the LHC, you should be clear about your likelihoods, okay? Now, the problem, so what you want is the probability of getting that data in theory 1 and the probability of getting that data in theory 2, okay? I could make this a little bit better written, because P's look like D's. And in principle, what I set up here was you just calculate the likelihood. I mean, if you have a well-posed theory, it should make a statement about what is the probability of getting different data. Sadly, in the real world, you very often face theories like these, which are not well posed, okay? Theory 1 is not a specific model of grand unification and symmetry breaking and the whole bit. Any specific model will make a prediction. either probability 1 or probability 0, that supersymmetry is going to be located at the LHC. But this is not like that. The idea that supersymmetry exists in some model is a wide variety of possible worlds, right? There's a lot of different kinds of ways that supersymmetry could exist. Maybe it exists, but it's broken at the Planck scale. So it exists, it's part of nature, but it's not visible at the Large Hadron Collider. Maybe it exists, but it's broken right there at the electroweak scale, in which case you would expect to observe it at the Large Hadron Collider. So a certain amount of judgment comes into calculating these likelihoods, even though they're supposed to be perfectly well defined. So it's a sad fact. So let's say that what you would have guessed before we turn the Large Hadron Collider on is that if supersymmetry exists, we probably would see it. Let's say you thought there was an 80% chance that you would see supersymmetry at the LHC. So the probability of not seeing it, the likelihood of not seeing it, you write as 0.2, okay? And the likelihood of not seeing supersymmetry, if there is no supersymmetry, is 1. These are likelihoods. They don't need to add to 1, okay? They could both be 1 in different theories, in which case, if the likelihoods are the same in different theories, then Bayes' theorem does not move your priors into different posteriors at all. But okay, then we calculate the probability of getting that data in the whole set of possible theories, right? The probability of getting that data, you did not see supersymmetry, is, well, the probability of getting that data in theory 1, which is 0.2, times the prior probability for theory 1, which is 0.9, plus the probability of getting that data in theory 1, which is 1, times the prior probability, theory 2, which is 1, times the prior in theory 2, which is 0.1. And I've done this ahead of time. This is 0.28. You can check my math at home. My prior that my math is correct is about 50%. So that's the probability of getting the data given your priors and your likelihoods. And therefore, the probability that theory 1 is true, the probability that supersymmetry is still lurking out there to be found, given that you haven't found it at the LHC, this is kind of fun that we can actually calculate this. Well, what is the formula? Where's Bayes' law? The likelihood of that in theory 1 times the prior for theory 1. So that is 0.2 times 0.9 divided by the total probability of that data, 0.28. And I worked this out and I get 0.64. Okay. So I started the day 20 years ago. I thought there was a 90% chance that supersymmetry was out there somewhere lurking to be found as a part of the fundamental laws of nature. I turned the LHC on. I didn't see it. I was disappointed. But I'm still left with what I would write as a 64% chance that supersymmetry is still out there. So on the one hand, less by a substantial amount than I started with. On the other hand, still greater than 50%. This is supposed to explain why there's plenty of physicists out there who think that it's still very likely that supersymmetry is part of nature. Either we'll find it soon, or at the next big collider, or we're not going to find it because it's broken at the Planck scale, but it's still out there. Anyway, this is an example of good Bayesian reasoning. The idea is, a Bayesian inference is that this is the right way to think about all probabilities. You should be honest about your priors. And this is why people start arguing frequentists versus Bayesians. Frequentists really want probabilities to be objective, okay? They really want to imagine that I could have flipped the coin an infinite number of times and find the frequency with which it came up heads or tails. Bayesians say I should admit that probabilities are just not objective, and I should admit that I have priors which are subjective. And the frequentists say, well, your priors could be anything. You could get any answer you want. And the Bayesians will say, yes, I could by picking dumb priors. But number one, real scientists don't pick dumb priors. Like, they might disagree, but they shouldn't be wildly inconsistent. And number two, we should be able to agree on the likelihoods given those theories. Maybe we can't, but at least that's something we should be able to do. And so a good Bayesian scientist, when they write a paper with some new data that points toward a result, they will emphasize the likelihoods rather than the priors or the posteriors, because those are more subjective. Anyway, it's a useful way to help us think about quantitatively how to locate ourselves in the set of all possible worlds, and it's a good way of thinking about how probability can be made compatible with a world even if the fundamental laws of physics are deterministic. We don't know if they are. I think that they probably are, but that's just my prior.